Hello, hello, hello. This is Nicholas on this lovely Wednesday afternoon making a special video dedicated to one of my dearest of fans, Mackenzie Meckler, talking to you today about the Poisson distribution, more commonly said in the States as the Poisson distribution. Now, the Poisson distribution is kind of one of the later types of distributions that you'll talk about in a statistics class, and for good reason. So typically, you'll first talk about a normal distribution, and then, maybe later you'll talk about a Poisson distribution. Now, Poisson distributions are good for modeling events such as, say, for example, you've got, a shop, and they say that they sell on average 200 Major League Baseball trading cards a day. They're a really busy shop. And then you want to find out, okay, well, what's the probability that I sell more than 300 or more than 400 Major League Baseball trading cards that particular day? And so, businesses like actuaries and things like this will use the Poisson distribution in order to be able to see how much they should, understock or overstock to prepare for a busy season or things like this. Now, we call the mean, mu, we call it lambda with a Poisson distribution. And so here is a couple plots of the general shape of a Poisson distribution. So lambda equals 1. We see that it's really heavily right skewed. When we start out with small means in the Poisson distribution, it's very heavily skewed to the right. And now as we increase the mean mu, this here appears to be approximately normal. And that's true. The bigger your mean lambda is in a Poisson distribution, the more closely it looks to a normal distribution. Now, the Poisson distribution is actually defined as, they use K in this picture straight from Wikipedia, but the probability that, let's say, x is equal to K, in other words, x being our random variable, is equal to, we say it's lambda to the K, e to the negative lambda over K factorial. Now, another thing to keep in mind here is that based on this picture, and in general, the Poisson distribution is discrete. It's not a continuous distribution, so it would certainly not apply for things like, say you got a golf ball manufacturer, and the mean diameter of the golf balls is, let's say a table tennis ball manufacturer, and the mean diameter of the table tennis balls is 40 millimeters. What's the probability they manufacture one that's greater than 40.1 millimeters? The Poisson distribution would not apply there because the diameter of the table tennis balls is a continuous spectrum, not a discrete spectrum. Now, another thing that this implies is that obviously, since it's a type of probability distribution, then we know that the sum from k equals 0 to infinity of lambda to the k e to the negative lambda over k factorial must be equal to 1. Because the probability that in other words, what this sum means is that you're summing up the values, the discrete values that you get for this Poisson distribution from start up until infinity, we're at asymptotes, And so when you do that, the probability that something happens is 1. In other words, summing up all possible events gives you a total of 1. And now this is true in the probability sense, but there's also another really intuitive sense in which this is true. That helps me at least remember this particular formula for the Poisson distribution. So I didn't really plan this, but I guess it follows nice, is that if you look back at my I factorial video, I used what was called, and I have a number of videos on this as well, I used what was called the gamma function to analytically continue the factorial function for non-natural numbers. So the gamma function, gamma of x, is equal to the integral from 0 to infinity of, and guess what? It's e to the negative x, x to the t minus 1, or t, x to the t, d, I should have done gamma of t. Gamma of t is equal to the integral from 0 to infinity of e to the negative x, x to the t, dt. So in other words, give me a t, dx. There we go. So in other words, plug in a t, right? And if you just evaluate that integral, you're going to get also t factorial. So it's a way of extending the factorial function for non-negative, or for not just non-negative integers. Now, if we look at this, right, roughly speaking, this here and this here are matching. In other words, this numerator of the sum is just the integrand in the gamma function. And then the denominator is just what the gamma function was based off of. So what that tells us is that as we go to infinity for large values of k, the sum essentially becomes the sum from k equals 0 to infinity of, oh gosh, I didn't write quick enough, k equals 0 to infinity of k factorial over k factorial. Because that is what the gamma function was based on, was the factorial function. Now, that's also another sense of why that sum is equal to 1 there. Okay, so now there are a couple assumptions that we make with the Poisson distribution. So the first assumption being that the events are independent of one another. Having one event happen does not influence the probability of a second event happening. So for example, well, let me say the second one first. The second is that the probability of any particular event occurring is the same for all events. In other words, the events are happening randomly. So a situation that you couldn't use the Poisson distribution for most likely is, for example, we're going to college soon. If you're going to UF and you say that, well, the mean number of students that are entering the rights student union at a particular time is 5 or something, I don't know. What's the probability that you got like more than 10 students entering at like 7 or something? That would be a situation where you probably would not want to use the Poisson distribution, because likely the events happening are not random. For example, it's probably pretty predictable that people are going to be entering the union when classes are off, and when classes are on, they're going to be in class. They're not going to be going to the student union. So the event is influenced by external factors, and it would not be a good idea to use the Poisson distribution there. And maybe there's a degree of like peer pressure if we're talking about the independent part. Maybe if there's a bunch of people already in the student union, the people that aren't in it feel left out, and then they want to go too. So you got to be careful about the independence and the randomness of the events in the situation you're modeling. Now, another important tidbit about the Poisson distribution is that the mean is also equal to the variance. And so therefore the standard deviation is equal to just the square root of the mean. Now I won't go into too much detail about that particular fact. It does take a bit to prove, but I will say that finding the mean can be done, say in a problem they give you various probabilities, then finding the mean from there can be relatively easy. So let's say, for example, you're told that, I don't know, the probability let's say, the probability that x is equal to 2 plus 5 times the probability that x is equal to, 5 times the probability that x is equal to 1 plus 6 times the probability that x is equal to 0 equals 0. So, say we're given that, for example. And by the way, IB did give us that in like 2019 or whatever it was. And they asked you to find the mean. So how could we do this? Well, just go back to the definition. The probability that x equals 2 is the same thing as writing that lambda squared e to the negative lambda over 2 factorial plus 5 lambda e to the negative lambda over 1 factorial plus 6 lambda to the 0, which is 1, e to the negative lambda over 0 factorial, which is 1, equals 0. And so really what they're doing is they're just giving you a quadratic in lambda to solve. So because the e to the negative lambdas go away, and what we get lambda squared over 2 plus 5 lambda plus 6 equals 0. So lambda squared plus 10 lambda plus 12 equals 0. And then you'd have to solve for lambda there. I think I've actually... No, that one. So lambda would be equal to the... it would be equal to negative 10 plus or minus the square root of 100 minus 48 over 2, which is negative 10 plus or minus square root 52 over 2. And I think that there's a factor of 4 that you can pull out of 52. What's that? 4 times 52 divided by 4, that's 13. So that would be equal to negative 10 plus or minus square root 13. So you can see that you can find lambda given statements about probabilities, and finding the actual cumulative probabilities, you would usually rely on a calculator for that. So for example, let's talk about this blue distribution right here where lambda is equal to 10. And let's say you wanted to find the probability that x is greater than 15. So that would be, well, actually I shouldn't have drawn it like that. It would really be, because it's a discrete distribution. So you're adding up those areas there. And the areas, as you go farther, would go to 0. So usually you would rely on your calculator to do that because you probably don't want to sum up, you'd actually be summing up infinitely many values. And normally what you do, if you're talking about the probability that x is greater than some number, because this distribution does go on to infinity, you would normally, and when you're using your calculator like a TI-84, you would write that this is 1 minus the probability that x is going to be at most 15, or less than 15, because that is just a finite number of calculations the calculator has to do, namely 14 of them. So that's a basic introduction to the Poisson distribution, and it is very much connected to the gamma function. So, and one other thing I wanted to mention is that sometimes there is a bit of a hiccup as to when you are supposed to use the Poisson distribution and the binomial distribution. So remember that when you have a binomial distribution, and normally IB would tell you, I would think anyways, because it usually can get pretty particular. Binomial distribution, the way I've always remembered it, if something is binomial or not, is I use from stats class, the one thing I remembered was bins. So if your outcome is binary, in other words, it either happens or it doesn't, the events are independent of one another, you're given a specific number of events, and you're given a probability of success, a specific probability of success, and therefore a probability of failure, then if you can use this, you could use a binomial distribution. And then also realize that a binomial distribution, like a Poisson distribution, is discrete. We're talking about, for number of events, we're talking about discrete numbers, right? And if you listen kind of carefully to my scenarios where a Poisson distribution would work, a binomial distribution would have also worked too, really. So the general way to distinguish between when to use the binomial distribution and when to use the Poisson distribution is that with a Poisson, you're talking about average probabilities. So if your question is asking about the average probability that an event happens, per unit, per day, or whatever, and you're given the mean, then you should go with the Poisson. But if you're talking about with binomial distributions, you'd use it if you're talking about exact probabilities. So, if you want to find the probability that this event happens, say 10 times out of 100 or 99 times out of 100, then you're going to want to use the binomial distribution instead. But in both cases, they'll approximate each other fairly well, especially for larger and larger numbers of events happening. And so I believe with that, we're done.